but it is very applicable to the 62 industrial waters that EPA has identified, and that includes food processing and farming. So right now we're working with Del Monte out in California, because all of a sudden they are have a flow that's almost 1 million gallons a day when they're really rolling, and the state of California has imposed regulations that if they don't cut that water use by 25%, they're subject to a $10,000 a day fine.
Yeah, that's why.
What we are going to do for them is recycle all of their water,
Yeah.
so that they use almost none.
Great,
And now this water
that's what we need.
This water is the raw water from an industrial laundry. Doesn't look like it's very nasty, and it's not very nasty. But the problem is, right now, all they can do with it is dump it back to the sanitary sewer. Well, it's okay to put it in the sanitary sewer, but they have to pay for the water incoming, and it turns out that you always, if you look at it may not be visible in your water bill, but you're always paying for the water that you put back in the sanitary sewer as well. So if you can replace the water that you're trying to use, and the cost of water to commercial laundries is about 50% of their total costs. If we can recycle their water, we have the opportunity to really reduce their costs.
Sure, yeah.
And that's the reason I'm headed to Atlanta this week, because that water belongs to a commercial laundry in Atlanta that has a number of commercial laundries throughout the Southeast. And today they're using chemicals. And the chemicals that we replace, and this is what's significant. We replace alum and we replace ferric chloride. Well, we've been using ferric chloride for about 150 years. We've been using alum for about, I don't want to exaggerate, only about 4,000 years. But people have known about using alum for a very long time. And all alum is an aluminum compound. Alum is Al2SO4 3. When you dump this into the water, what happens? It splits into two Al+++ and a bunch of junk. Guess what? That's exactly what we're doing here. So we're replacing alum with this process, and that's all we do. Nothing magic about that, except that alum is a great water processor, but we're better. And the reason that we're better is that alum is not a biocide, but because of the electrical fields here, we're a biocide and we actually kill germs. So I can drink that water that we just, and I don't even know what's in the water, because it's water I just picked up off the street. But I do know that I've tested it enough that I can drink that water safely.
Wow.
So we can use aluminum here as our anode. We can use iron, or we can use zinc. Well, what happens when you put ferric chloride in the water? It breaks into chlorine and iron. So you wind up with 3 negative chlorines and 1 iron that's positively charged with missing 3 electrons. Either one of those, depending on what you're trying to treat, can be perfect. Sometimes it takes both, in which case it's easy enough to do. We either put 2 reactors out there, or we put an iron plate and an aluminum plate on our little reactor. And we've done both of those for a number of years now. So, and that's really all there is to the technology. So the real question is, okay, big deal. Why have people been using it for 130 years, and why isn't everybody using it every day? And the reason is simple enough. The reason is that once you start this process in the way that I've done it here, where these are just flat plates in your water, what happens is that you begin to get aluminum oxide. Remember I told you aluminum oxide was about one of the hardest substances around. Well, in a few hours, 4 to 10 hours, you'll get a coating of aluminum oxide on this aluminum plate that cannot be removed short of machining or holding it in hydrochloric acid, pure hydrochloric acid, for several hours. So that's what has made this system fail for 130 years. People that are doing the science, they do a little bitty thing like this, except that they use flat plates. They don't have a rotating plate. And they run it for a few hours and demonstrate that it works, write up all the chemical equations, and publish some wonderful papers. And so that's the really good news. And for us, the other good news is that it's been very difficult to solve this problem. So what do we do, and what's the purpose of what we're doing? The purpose of rotating the plates, we started out doing that, and we started out doing that in 2004. And about 2005, after we built this particular rotating plate unit, and this is nothing but a Tesla pump. Tesla patented this pump idea in 1920. But what it does, what's important is the exposure time of the water to this aluminum. What this allows us to do, it allows us to circulate the water for as long as we want to circulate it. So with small, very, very small plates, we can get any exposure time that we would like. You know, I could obviously run that for 2 hours if I wanted to. So I could expose the water to this chemical for 2 hours if I needed to. And if you're using flat plates, typically they have to have much larger plates in order to have that exposure time. So
how many times have they rotated
we're rotating about 300 RPM.
before you have to get rid of the plate?
Oh, this unit will probably run at the rate that we saw it for about a month. The big units that we're building have 12 plates, 24 inches in diameter.
Oh, that's big.
And note, if you probably didn't pay too much attention, but I'm using 20 amps here of current. The big units use 500 amps.
So in size, you know, it's like how?
That's right.
Yeah. Okay.
And this is strictly, how much metal we put in here is strictly a function of how much current we put into that plate. More current, more metal.
Okay.
So, and for every 3 electrons that we put into the plate, we get 1 aluminum atom. And it's very simple to compute how much aluminum you get based on the amount of current. We put a current meter right here, put an ammeter here. We measure the current, we know exactly how much aluminum. That was exactly what I was doing down here. When I turned this on, this is my current. Okay, so I always know exactly how much current I'm putting into the device. The voltage isn't important, except that the saltier the water, the lower the required voltage, the less power it takes. So right now with 8 volts and 20 amps, we're using 80 watts.
Yes.
Hello.
Hi.
Hello, how are you?
Hi.
Sorry to interrupt.
No problem.